The ocean is breathing. At first, it looks like mist rising from cold water at dawn, but it is not dawn. The horizon glows a dull copper even though the sun has barely climbed above it. The air feels heavy, swollen with warmth that does not fade through the night. Waves roll in slow motion, their crests blurred by faint threads of steam. Seabirds circle low, confused, their shadows warped against a shoreline that feels warmer than skin. Across the planet, thermometers whisper the same quiet truth. Average temperatures have crept upward, not in spikes or disasters, but in a steady, relentless climb. Forests release a sharper scent. Asphalt softens under tires. Glaciers retreat into memory. Something fundamental has shifted. The sky no longer carries the same blue. It leans toward white at midday, a washed brightness that presses against the eyes. Sunlight feels heavier, more direct, as if the distance between Earth and its star has thinned. At night, the darkness is shallower. The air holds the heat, refusing to let it go. The oceans are not boiling, not yet, but in the shallows, instruments detect an unfamiliar rhythm. Surface layers grow warmer year after year. Evaporation increases. Clouds gather thicker, higher. Storm systems grow slower, heavier, drenched with moisture drawn from seas that no longer cool as they once did. No comet has struck. No supervolcano chokes the sky. The change comes from 150 million kilometers away. Deep inside the sun, hydrogen atoms fuse into helium, releasing energy that began its journey thousands of years ago in the crushing core. That fusion has powered every sunrise in human history. It feels eternal. It feels stable. But stability in stars is a slow balancing act between gravity pulling inward and nuclear fire pushing outward. That balance is shifting. The sun is not exploding. It is aging. Like all stars of its mass, it was born in a cloud of gas and dust about 4.6 billion years ago. It ignited, entered its long adulthood, and settled into a phase astronomers call the main sequence. In this stage, hydrogen fusion in the core produces a steady output of energy. For billions of years, that output has been remarkably consistent. But consistent does not mean constant. Since its birth, the sun has brightened by roughly 30%. It shines more intensely now than it did when Earth first formed. The difference was subtle across human timescales, invisible across civilizations. Yet, over billions of years, that slow increase has reshaped climates, melted ancient ice, and nudged the chemistry of the atmosphere. Now, the increase continues. Every second, the sun converts about 4 million tons of matter into energy. As hydrogen in the core fuses into helium, the composition changes. Helium accumulates. The core contracts slightly under gravity, growing hotter and denser. A hotter core fuses hydrogen faster. Faster fusion produces more energy. More energy means greater luminosity. It is a feedback that unfolds across eons. On Earth, the consequences arrive gradually. Average global temperatures tick upward, not by degrees in a decade, but by fractions of a degree across centuries, then millennia. Ice sheets thin, polar oceans open into dark water that absorbs more sunlight. The planet reflects less and absorbs more. Clouds thicken in some regions, thin in others. Weather patterns drift. Tropical zones expand toward the poles. Regions that once knew snow see only rain. Regions that knew rain feel dryness settle into their soil like a permanent season. The oceans continue to breathe out vapor. Evaporation increases. Water molecules rise, carrying heat upward. The atmosphere grows richer in water vapor, itself a powerful greenhouse gas. Heat that once escaped more easily into space lingers a little longer. Still, life adapts. It always has. Species migrate, ecosystems rearrange. Humans build cooling systems, underground cities, orbital habitats perhaps, but adaptation requires time, and the sun offers less and less of it. Tens of millions of years pass. Continents shift under the slow churn of plate tectonics. Mountain ranges rise and erode, oceans open and close. But above it all, the sun shines brighter still. Global average temperatures climb several degrees higher than anything in recorded history. Tropical oceans approach temperatures once seen only in geothermal vents. Coral reefs bleach and vanish. Phytoplankton populations decline in warming surface waters, disrupting the base of marine food chains. Carbon cycles struggle to compensate. Weathering of rocks accelerates, drawing carbon dioxide from the atmosphere in chemical reactions that lock it into minerals. This natural thermostat has regulated Earth's climate for billions of years, but it operates slowly, and the increasing solar luminosity pushes steadily forward. Hundreds of millions of years unfold like quiet chapters. At some point, roughly 1 billion years from now, models suggest that solar luminosity may be about 10% higher than today. 10% sounds small. It is not. The additional energy pushes Earth's climate beyond thresholds that have kept liquid water stable on the surface. Average global temperatures rise toward levels that make complex life difficult. The tropics become lethally hot for unprotected organisms. Wet bulb temperatures approach limits beyond which mammals cannot cool themselves through sweating. Oceans warm deeply. Evaporation intensifies. The atmosphere thickens with water vapor. Clouds grow more persistent, trapping heat. A slow march toward instability begins. In shallow seas, steam becomes more visible at sunrise, not a rolling boil but a constant haze. The horizon blurs under layers of moisture. Rain falls in heavier bursts, then stops for longer dry stretches. Deserts expand. Forests retreat toward higher latitudes and elevations. Humanity, if it still exists, may retreat underground or into engineered habitats. Perhaps vast sunshades orbit between Earth and the Sun, reducing incoming radiation. Perhaps orbital mirrors redirect light away. Or perhaps the species that once named constellations is long gone, replaced by descendants adapted to heat or by silence. The Sun continues its quiet brightening. 1.5 billion years from now, the additional luminosity could trigger a profound transformation. Surface temperatures may climb high enough to destabilize the oceans permanently. Increased evaporation loads the atmosphere with more water vapor. Water vapor traps heat. More trapped heat causes more evaporation. This is the beginning of a runaway greenhouse effect. At first, the term sounds dramatic. In reality, it is a physical process. As solar input increases, the planet warms. Warmer air holds more water vapor. Water vapor is a greenhouse gas. The greenhouse effect strengthens. The planet warms further. At a certain threshold, outgoing infrared radiation can no longer balance incoming solar energy. The system runs away. Oceans begin to shrink, not in a single violent boil, but in a persistent evaporation that exceeds precipitation and recycling. Upper layers of the ocean heat, releasing more vapor into an atmosphere already thick and heavy. Clouds cover vast regions, reflecting some sunlight, but trapping even more heat below. The sky changes color. It loses the deep blue of scattered light and becomes a brighter, whiter dome, diffused by water vapor. Sunsets turn fierce orange and crimson, filtered through thick layers of moisture and haze. As the oceans recede, coastlines creep outward. Continental shelves emerge as steaming plains. Salt flats stretch across former seabeds. Marine life collapses. Without stable surface oceans, complex ecosystems unravel. Water vapor rises high into the atmosphere, reaching altitudes where ultraviolet radiation from the sun splits molecules apart. Hydrogen escapes to space, atom by atom, too light for gravity to hold indefinitely. Oxygen reacts with surface rocks, oxidizing continents on a planetary scale. Earth begins to lose its water permanently. 2 billion years from now, the surface may resemble a world once imagined only in science fiction. Average temperatures soar well above the boiling point of water at current atmospheric pressures. But pressure is no longer current. With oceans largely evaporated, the atmosphere becomes a thick envelope of steam and other gases. At high pressures, water can remain liquid above 100 degrees Celsius. But as hydrogen escapes and total water inventory declines, pressure and composition shift. Eventually, surface conditions cross into a regime where stable liquid water cannot exist at all. Lakes vanish. Rivers dry into canyons filled with mineral crust. The last pockets of surface water retreat into deep underground reservoirs, then flash to vapor as heat penetrates further into the crust. The continents crack under thermal stress. Rocks expand and fracture. Chemical weathering accelerates in strange ways, driven by extreme heat and dense atmospheric chemistry. Volcanic activity continues as long as Earth's interior retains heat from its formation and radioactive decay, but even that internal warmth becomes secondary to the relentless solar blaze. Life as we know it cannot survive these conditions. Microbial extremophiles might cling to existence deep underground for a time, sheltered from surface infernos. But the biosphere that once painted Earth green and blue fades into memory. The planet does not explode. It does not shatter. It simply becomes hostile to complexity. Billions of years continue to pass. In the sun's core, hydrogen grows scarce. Helium accumulates until fusion in the central region slows. Without sufficient hydrogen pressure to counteract gravity, the core contracts further. Contraction raises temperatures even more, igniting hydrogen fusion in a shell surrounding the inert helium core. This new configuration releases more energy than before. The outer layers of the sun respond by expanding. As they expand, they cool slightly in surface temperature, but increase enormously in total luminosity because of their vastly larger size. The sun begins its transformation into a red giant. From Earth's perspective, if any perspective remains, the sun swells in the sky. It grows larger, brighter, redder. Days become searing arcs of light. The year remains the same length, but each orbit carries the planet through a furnace. 3 billion years from now, solar luminosity may be dozens of % higher than today. Surface temperatures on Earth are beyond any natural resilience. The crust bakes. Remaining volatiles are stripped away. The atmosphere, once rich with nitrogen and oxygen, thins and changes composition as lighter molecules escape and heavier ones react with surface minerals. As the sun ascends the red giant branch, its radius expands dramatically. Calculations suggest that in roughly 5 to 7 billion years from now, the Sun's outer layers could extend outward to near or beyond the current orbit of Earth. There is uncertainty. As the Sun loses mass through stellar winds, Earth's orbit may drift slightly outward. That outward drift could, in theory, spare the planet from being physically engulfed, but spared does not mean saved. Long before the expanding solar atmosphere reaches Earth's orbit, the planet's surface will have been sterilized, melted, reshaped. Oceans gone, atmosphere stripped or transformed, crust possibly partially molten under the intense radiation. If engulfment occurs, Earth will spiral inward through drag in the Sun's extended atmosphere, eventually disintegrating, its materials mixed into stellar plasma. If it avoids direct engulfment, it will remain as a scorched, airless rock orbiting a bloated red star, its surface temperature comparable to the surface of present-day Mercury or hotter. Imagine the final sunrise. The Sun fills a third of the sky, a vast red disk mottled with darker patches of convection cells larger than continents once were. The light is not the gentle yellow-white that once warmed forests. It is a deep copper glow that bleeds across a horizon of blackened rock. There are no oceans to reflect it, no clouds to scatter it into soft gradients. The sky, if any atmosphere remains, is thin and tinted by residual gases. Shadows are sharp, elongated, trembling in heat distortions, rising from a surface cracked like pottery. Time feels different here. Days may be shorter or longer depending on tidal interactions and orbital evolution, but time for observers has long since ended. No eyes watch, no instruments record. The last sunrise may pass unnoticed. Eventually, the Sun's outer layers will drift away entirely, forming a planetary nebula, a glowing shell of gas expanding into interstellar space. The core left behind will contract into a white dwarf, a dense ember roughly the size of Earth, but containing half the Sun's original mass. That white dwarf will shine with residual heat, gradually cooling over trillions of years. If Earth survives as a remnant rock, it will orbit this fading star in darkness, punctuated by a small, brilliant point of light. Surface temperatures will plummet as luminosity drops. The once burning world will freeze into a silent cinder. How long until Earth burns? In human terms, the answer feels abstract. Hundreds of millions, billions of years. Timescales so vast that civilizations rise and fall in less than a blink compared to them. Yet, the process has already begun. The Sun today is slightly brighter than it was yesterday, though the difference is immeasurable to human senses. Fusion continues. Helium accumulates. The core contracts by imperceptible amounts. The balance shifts atom by atom. Earth has existed for about 4.5 billion years. Complex life for only a fraction of that. Humans for an almost negligible instant. The window of habitability around a star like the Sun is not infinite. It is a phase, a middle chapter between frozen beginnings and fiery endings. The oceans that now steam gently in our imagined opening are not yet at that stage, but one day, far beyond any current lifetime, they will be. The story of Earth burning is not a sudden catastrophe. It is a slow crescendo written in the physics of stellar evolution. Gravity and fusion, pressure and radiation, chemistry and time. There is a strange comfort in its predictability. Unlike asteroid impacts or supernovae, the aging of the Sun follows well-understood equations. Models of stellar structure confirmed by observations of countless other stars at different stages of life map out the path ahead with sobering clarity. We look at red giants scattered across the galaxy and see our future. We observe white dwarfs cooling in the dark and see our sun's eventual fate. And yet, standing on a beach today, feeling the warmth of sunlight on skin, it is almost impossible to imagine that this same star will one day strip oceans from rock. The ocean breathes quietly under the present sun. It reflects blue light. It carries currents that regulate climate. It cradles life in forms both delicate and immense. 1 billion years from now, that breathing may become a constant exhalation into space. 2 billion years from now, the breath may have ceased entirely. 5 billion years from now, the very ground beneath any hypothetical observer may glow under a red giant sky. And then, after the fire, silence. The last sunrise does not announce itself. It arrives like every other, following the rotation of a planet that no longer hosts life. Light spills across desolation. Rocks absorb photons that left the solar core thousands of years earlier. Energy radiates outward, indifferent, inevitable. There is no tragedy in the sun's aging. It is the natural arc of stellar existence. But there is poignancy in knowing that the warmth enabling thought, memory, and wonder is temporary. Earth will burn, not tomorrow, not in any era relevant to current humanity, but in the fullness of cosmic time. Until then, the oceans continue to breathe. The sky remains blue. The sun shines with a brilliance that feels constant. Deep in its core, the future is already unfolding. The warmth does not retreat at night anymore. Darkness falls, but the air remains heavy, saturated with the memory of sunlight. Oceans release their stored heat in slow exhalations. Across equatorial regions, the sea surface temperature no longer dips enough to restore balance. The planet radiates energy into space, but not as efficiently as it once did. The reason lies 150 million kilometers away. A star like the Sun lives most of its life in a stable state called the main sequence. In this phase, gravity pulls inward with immense force, attempting to compress the star further. Opposing that collapse is the outward pressure generated by nuclear fusion in the core. Hydrogen nuclei collide under extreme temperatures and pressures, fusing into helium and releasing energy according to Einstein's equation. That energy travels outward through radiation and convection, eventually escaping as sunlight. For billions of years, this balance appears steady, but it is not perfectly constant. Each fusion reaction changes the composition of the core. Hydrogen is gradually converted into helium. Helium does not fuse under current core conditions in a star of the Sun's mass. It accumulates. As helium builds up, the core becomes denser. Gravity compresses it slightly more. Compression raises the core temperature. A hotter core increases the rate of hydrogen fusion in the surrounding layers. Increased fusion means greater energy output. The sun brightens, not abruptly, not in flares or violent pulses that threaten Earth overnight. Instead, luminosity increases by roughly 10% every billion years. That small percentage, stretched across geological time, transforms climates and landscapes. 100 million years from now, the difference will be subtle but measurable. Earth's average temperature will creep upward. Ice caps that might still exist will shrink further. Subtropical regions will extend toward the poles. Rainfall patterns will shift as warmer air holds more moisture. 300 million years from now, the increase in solar radiation will intensify evaporation rates globally. Oceans will lose more water to the atmosphere each year. Water vapor will accumulate in the lower atmosphere, enhancing the greenhouse effect. Water vapor is not just a byproduct. It is a powerful regulator of climate. It absorbs infrared radiation emitted from Earth's surface, trapping heat that would otherwise escape into space. As the sun brightens, more water evaporates. As more water evaporates, more heat is retained. This feedback amplifies warming. Earth has experienced greenhouse climates before. During ancient periods, tropical conditions extended nearly pole to pole. Crocodile-like reptiles once inhabited regions that are now frozen tundra, but those climates unfolded under different solar conditions and atmospheric compositions. The coming changes will be driven by the fundamental evolution of the star itself. 500 million years from now, solar luminosity may be about 5% higher than today. That increase alone could raise global temperatures by several degrees Celsius beyond pre-industrial levels. Even small changes in global averages can correspond to dramatic regional extremes. Forests may retreat toward higher latitudes. Many plant species rely on specific temperature and precipitation ranges. As these ranges shift, ecosystems will reorganize. Some species will adapt through evolution across millions of years, others will disappear. Marine ecosystems will struggle under warming surface waters. Warmer water holds less dissolved oxygen. Stratification between warm surface layers and cooler deeper waters may reduce nutrient mixing, impacting phytoplankton growth. The base of the marine food web will weaken. As evaporation continues to intensify, cloud formation patterns will change. Some regions may see persistent cloud cover that reflects a portion of incoming sunlight, but clouds also trap outgoing infrared radiation. The net effect depends on altitude, thickness, and distribution. Over hundreds of millions of years, these complex interactions settle into a new equilibrium each time solar input rises. But the equilibrium point keeps shifting upward. 1 billion years from now, models suggest the sun's luminosity could be roughly 10% greater than it is today. At that level, Earth may approach a critical threshold. Surface temperatures in tropical regions could reach sustained levels above 50 degrees Celsius. Wet bulb temperatures, a measure combining heat and humidity, may exceed the limit at which mammals can cool themselves through sweating. Even simple exposure to air could become lethal for unprotected organisms. Plant life would face intense stress. Photosynthesis depends on carbon dioxide concentration and temperature. As temperatures rise, chemical weathering of rocks accelerates, drawing carbon dioxide out of the atmosphere and locking it into carbonate minerals. This long-term negative feedback has helped stabilize Earth's climate for billions of years. But lower carbon dioxide concentrations also limit photosynthesis. As the sun brightens and weathering intensifies, atmospheric carbon dioxide could fall to levels too low to sustain many plant species. Forests may thin, grasslands may struggle. The oxygen production that once shaped Earth's atmosphere could decline. Meanwhile, oceans will continue to warm. Increased evaporation will feed more water vapor into the atmosphere. The upper atmosphere, once relatively dry, will begin to hold greater concentrations of moisture. At high altitudes, ultraviolet radiation from the sun splits water molecules into hydrogen and oxygen. Hydrogen, being extremely light, can reach escape velocity and drift into space. This process is slow at present, but as more water vapor reaches higher layers, hydrogen loss accelerates. Every hydrogen atom lost represents a fragment of Earth's water inventory permanently removed. Over tens to hundreds of millions of years, this loss accumulates. As the greenhouse effect strengthens, outgoing infrared radiation struggles to keep pace with incoming solar energy. Normally, as a planet warms, it radiates more energy into space. This negative feedback helps stabilize temperature, but water vapor complicates the balance. It absorbs strongly in infrared wavelengths, reducing the efficiency of cooling. If solar luminosity continues to increase beyond certain thresholds, Earth may cross into a moist greenhouse state. In this regime, the lower atmosphere becomes saturated with water vapor, and significant amounts reach the stratosphere. Surface oceans would not vanish instantly. Instead, evaporation would outpace replenishment over extended timescales. The hydrological cycle would accelerate, but net water loss to space would steadily reduce total ocean volume. 2 billion years from now, solar luminosity could be roughly 20% higher than today. Under such conditions, average surface temperatures might climb toward or beyond the boiling point of water at standard atmospheric pressure. However, atmospheric pressure would not remain standard. As oceans evaporate, atmospheric pressure initially increases due to added water vapor. High pressure raises the boiling point of water, so instead of a violent boil, oceans would gradually thin under a heavy, steam-rich sky. Clouds would likely blanket much of the planet, reflecting some sunlight but also trapping enormous amounts of heat. The sky would appear bright and diffuse. Sunlight would filter through layers of vapor, scattering into a constant glow rather than a clear beam. Rain would fall in extreme events, torrential and scalding, only to evaporate again shortly after reaching the surface. As hydrogen escapes to space and oxygen reacts with surface rocks, the composition of the atmosphere shifts. Nitrogen may remain as a dominant component for some time, but oxygen levels would decline as photosynthetic life disappears and oxidation of surface materials consumes available molecules. Eventually, as water inventory diminishes significantly, atmospheric pressure may decrease again. With less total water remaining, the greenhouse blanket may thin slightly, but by then, surface conditions will be profoundly altered. Continents will be exposed across vast former ocean basins. Sediments once buried under kilometers of water will crack under relentless heat. Salt deposits will crystallize across plains that once hosted coral reefs and fish. Volcanism may continue to release gases, including carbon dioxide and sulfur compounds, but without oceans to dissolve and cycle them, atmospheric chemistry will operate differently. Sulfuric acid clouds could form transiently, reminiscent of conditions on Venus, though exact outcomes depend on complex interactions. The comparison to Venus becomes increasingly relevant. Venus likely experienced a runaway greenhouse early in its history, possibly after losing surface water through similar processes. Its dense carbon dioxide atmosphere and high surface temperatures offer a cautionary example of planetary evolution under intense solar radiation. Earth's greater distance from the Sun has protected it for billions of years. But as the Sun brightens, the habitable zone moves outward. The region where liquid water can exist on a planetary surface shifts slowly away from the star. Earth, once comfortably inside that zone, drifts towards its inner edge, then beyond it. 3 billion years from now, the sun's luminosity may be 30% higher than today. At this stage, the classical habitable zone will have moved well beyond Earth's orbit. Mars, if it retains sufficient atmosphere, might temporarily pass through conditions more favorable for liquid water. Icy moons in the outer solar system could thaw, but Earth will be deep inside a region too hot for surface oceans. The oceans that once defined this world will be memories written in rock layers. The deep-sea trenches will be dry scars. The mid-ocean ridges will stand exposed as mountain chains across a desiccated globe. Surface temperatures may exceed several hundred degrees Celsius. Rocks near the equator could glow faintly under extreme heat during prolonged daylight. Thermal expansion and contraction cycles would fracture crustal plates, increasing seismic activity. If any life remains, it will exist far below the surface, insulated from the worst heat. But even there, geothermal gradients combined with high surface temperatures will push conditions beyond tolerable limits. Throughout this entire process, the sun will still appear stable in the sky, though gradually brighter and perhaps slightly larger. Its color will shift subtly as surface temperature changes during late main sequence evolution. The transformation from a life-supporting star to a world-destroying furnace is not marked by a single event. It is a slow escalation written into stellar physics. Every second that passes today brings the sun closer to exhausting the hydrogen in its core. The total hydrogen supply is vast, but finite. When the core hydrogen is finally depleted, fusion there will cease. Gravity will compress the helium-rich core further, heating it to temperatures sufficient to ignite hydrogen fusion in a surrounding shell. That shell-burning phase will dramatically increase energy output, but that stage belongs to the next chapter. For now, in this era spanning the next few billion years, the critical story is luminosity increase during the main sequence evolution. It is enough to strip oceans, collapse ecosystems, and sterilize a planet without any explosive drama. The oceans that breathe tonight under a familiar sun will not always do so. Their evaporation will accelerate. Their depths will shrink. Their molecules will drift into space as hydrogen escapes forever. The sky will thicken with vapor. The land will bake. The atmosphere will transform. And all of it will happen while the sun continues to shine with deceptive calm. This is not the end. It is the long, unfolding middle. The steady climb toward conditions from which there is no natural return. The heat that now feels gentle on skin carries within it the distant future of a burning world. The sky no longer clears. Morning arrives through layers of vapor that never fully dissipate. The sun is a blurred disk behind a luminous veil, its edges softened by a planet that exhales without rest. The air presses downward with weight. Heat does not spike and fade. It lingers, accumulates, saturates stone and soil until the ground itself feels alive with stored fire. The oceans are shallow now. Where there were once thousands of meters of cold darkness, there are hundreds. Continental shelves stretch wide and barren, exposed to a sky thick with steam. Former coastlines sit stranded inland as salt crusts form intricate white patterns across cracked mud. Rain still falls, but it no longer nourishes. It scalds. Water cycles upward in vast columns, rising into an atmosphere overloaded with vapor. Storm systems tower higher than any in Earth's ancient past, their clouds reaching into layers of air once dry and clear. Lightning flashes through dense curtains of moisture. Thunder rolls slowly, muffled by the heavy sky. The greenhouse effect has intensified beyond moderation. In a stable climate, a planet warms and responds by radiating more infrared energy into space. The relationship is balancing, almost elegant, but when water vapor dominates the atmosphere, that elegance falters. Infrared radiation emitted from the surface is absorbed, re-emitted, and trapped repeatedly. The escape of heat becomes inefficient. As solar luminosity continues its gradual rise, Earth crosses a threshold from moist greenhouse into full runaway greenhouse. The defining characteristic is not instant boiling, it is loss of equilibrium. Incoming solar radiation exceeds the maximum outgoing infrared radiation the planet can emit. Even if surface temperature rises significantly, the planet cannot cool itself sufficiently. Any additional heat forces further evaporation, which enhances the greenhouse effect, which traps more heat still. Surface temperatures climb relentlessly. 100 degrees Celsius is no longer an extreme, but a baseline in equatorial regions. Under high atmospheric pressures, water can remain liquid at temperatures above this point, but only temporarily. As hydrogen escapes to space, total water mass declines. Pressure fluctuates, stability erodes. Oceans retreat into shrinking basins. What remains becomes superheated brine, dense and mineral-rich. Marine life is long gone. No fish, no coral, no plankton drifting in sunlit layers. The final microbial organisms that once thrived in extreme vents have either retreated deep underground or vanished. The hydrological cycle collapses. Without vast oceans to evaporate and condense in balanced rhythms, rainfall becomes sporadic and violent. Eventually, as total water inventory decreases, rain ceases almost entirely. Clouds thin not because the planet cools, but because there is simply less water left to suspend in the air. The sky transitions from white vapor haze to a thick, oppressive atmosphere dominated by residual gases. Carbon dioxide levels fluctuate during this era. Early in the runaway process, increased weathering and reduced volcanic recycling may lower atmospheric carbon dioxide, but once oceans disappear, the chemical cycles that lock carbon into rock break down. Volcanic outgassing could rebuild a carbon-rich atmosphere over time, further amplifying heat. The comparison to Venus grows stronger. Venus today has surface temperatures around 460 degrees Celsius, hot enough to melt lead. Its dense carbon dioxide atmosphere exerts crushing pressure. While Earth may not replicate Venus exactly, the underlying physics of runaway greenhouse shares similarities. On Earth, as water is lost and oxygen reacts with crustal materials, the atmosphere may become dominated by nitrogen and carbon dioxide, with trace amounts of other volcanic gases. Without oceans to absorb carbon dioxide, concentrations could rise significantly. Surface temperatures could soar to several hundred degrees Celsius. Continents fracture under thermal stress. Rocks expand during long days of blistering heat and contract at night if temperatures drop at all. These repeated cycles widen cracks into chasms. Tectonic plates continue their slow drift, but subduction zones may weaken as water, which lubricates plate boundaries, disappears from the system. Mountain ranges erode under acid rains and extreme chemical weathering, then stand bare and jagged in dry heat once precipitation ends. Sedimentary layers once laid down in ancient seas lie exposed and oxidized. If any remnants of humanity or its descendants once existed during the earlier warming phases, they are gone now. No engineered habitat could survive indefinitely under a runaway greenhouse without continuous energy and maintenance. And even if technology persisted for millions of years, the scale of planetary transformation would overwhelm surface infrastructure. Underground refugees might endure longer. Deep beneath the crust, temperatures increase gradually with depth. Paradoxically, as surface temperatures rise, the gradient between surface and interior narrows. The zone where liquid water could exist underground shrinks. Eventually, even the deep biosphere succumbs. 2 to 3 billion years from now, Earth resembles a world suspended between fire and emptiness. The oceans are gone. The atmosphere, though thick, is dry compared to its steam-rich peak. Hydrogen has escaped in vast quantities, carrying with it the legacy of billions of years of oceanic history. Oxygen, once abundant and life-sustaining, has largely reacted away. Iron in the crust is oxidized. Rocks bear the chemical signature of a planet that lost its water to space. The sun, meanwhile, continues its quiet transformation. Inside the core, hydrogen is nearly exhausted. The rate of fusion in the central region declines. Gravity begins to gain the upper hand. The core contracts, increasing in temperature and density. Hydrogen fusion ignites more vigorously in a shell surrounding the helium-rich center. This shell burning releases more energy than the original core fusion alone. The outer layers of the sun respond. They expand. As the sun's radius increases, its surface temperature decreases slightly, shifting its color toward orange and red. But total luminosity increases dramatically because of the vastly larger surface area. The energy reaching Earth multiplies. 4 to 5 billion years from now, the sun begins its ascent into the red giant phase. From the surface of Earth, if any surface remains distinguishable, the sun swells in the sky. It appears larger day by day across geological timescales. Its light deepens into a copper hue. Convection cells, immense and turbulent, churn across its surface, visible as darker and brighter regions through a distorted atmosphere. Solar winds intensify. Charged particles stream outward in greater quantities. The expanding outer layers of the sun shed mass into space. As mass decreases, gravitational pull weakens slightly. Earth's orbit may drift outward in response. This outward drift offers a narrow possibility that Earth avoids physical engulfment, but avoidance does not equal survival. Long before the Sun's outer atmosphere reaches Earth's orbital distance, surface conditions will be catastrophic beyond comparison. Surface temperatures could exceed 1,000 degrees Celsius in some models during peak red giant expansion. At such temperatures, silicate rocks begin to melt. Lava flows not from volcanoes alone, but from crusts softened by pervasive heat. The distinction between solid ground and molten interior blurs. If Earth remains outside the sun's photosphere, it will still be bathed in intense radiation from a star hundreds of times more luminous than it once was. The atmosphere, if any remains, will be stripped away by solar winds and thermal escape. If Earth drifts inward due to tidal interactions with the sun's extended envelope, drag forces could cause orbital decay. The planet would spiral slowly into the outer layers of the red giant, disintegrating under tidal stresses and frictional heating. In that scenario, Earth's material would mix into stellar plasma, its atoms indistinguishable from the gas that once birthed it. If instead Earth survives as a remnant orbiting slightly farther out, it will be a scorched, airless rock circling a swollen red star. The Sun's red giant phase will not last forever. After helium ignites in the core in a process known as the helium flash, the Sun will stabilize temporarily, fusing helium into carbon and oxygen. Later, it will shed its outer layers entirely, creating a planetary nebula, a glowing shell of ionized gas expanding into interstellar space. At the center will remain a white dwarf. A white dwarf is not fueled by fusion. It shines from residual heat, gradually cooling over trillions of years. Roughly the size of Earth, but with half the Sun's mass, it will be unimaginably dense. If Earth's remnants still orbit, they will circle this fading ember in a darkening solar system. But before that quiet ending, there is the crescendo. The final million years before peak red giant expansion will see luminosity changes on shorter timescales. The Sun's radius may increase rapidly in astronomical terms. Earth's surface, already uninhabitable for billions of years, will endure the last surges of stellar intensity. Imagine the final sunrise. The horizon glows not with gentle yellow, but with a vast red wall of light. The Sun fills a significant portion of the sky, its edge distorted by convection and atmospheric turbulence. The surface below is cracked, blackened, perhaps partially molten. There are no oceans to reflect the glow, no forests to catch the light in leaves. Shadows stretch sharply across uneven rock. Heat ripples distort the view. The sky, if any atmosphere remains, is thin and tinted by residual gases. No life watches, no memory records. The Sun continues its cycle, indifferent to the fate of the world that once orbited comfortably within its habitable zone. How long until Earth burns? In one sense, billions of years. In another, the process is already underway. The Sun brightens by a fraction each million years. The habitable window narrows gradually. Earth's story of oceans, clouds, and life is a middle chapter in a much longer stellar narrative. Stars are born, shine, expand, and fade. Planets warm, transform, and sometimes perish in that light. The oceans that once breathed gently beneath a blue sky will not breathe forever. The sky that once scattered sunlight into deep azure will not remain that color. The warmth that now feels stable carries within it the certainty of change. And in the far distance of time, under a swollen red sun, or within its consuming envelope, Earth will complete its long journey from molten birth to burning end, leaving behind only atoms drifting in a galaxy that continues without pause. The red light deepens. Across spans of time so vast they erase all memory of oceans and forests, the Sun continues to swell. Its outer layers pulse outward in slow, unstable breaths. The star that once appeared constant now reveals its age in turbulence and expansion. From the orbit where Earth once moved through gentle seasons, the Sun dominates the sky. If the planet still circles beyond the star's outer atmosphere, it does so under conditions beyond anything it once knew. The surface is no longer a landscape, it is a furnace crust. Silicate rock softens at temperatures above 1000 degrees Celsius. Under prolonged exposure to red giant luminosity, entire regions of crust begin to partially melt. Lava no longer emerges only from volcanoes. The ground itself glows in places, thin films of molten rock spreading across fractured plains before cooling into dark glassy sheets. There are no tectonic cycles as once existed. Water, which once lubricated subduction zones and fueled explosive volcanism, is gone. The crust is rigid in some regions, weakened in others, but it no longer hosts dynamic balance of oceans and continents. It is a dry shell baking under an expanding star. The sun's mass decreases as powerful stellar winds carry away outer layers. This mass loss weakens its gravitational pull. Earth's orbit responds gradually, drifting outward over millions of years. The change is not dramatic in any single era, but over long intervals it becomes significant. This outward migration may save Earth from immediate engulfment, but tidal forces complicate the story. As the sun expands, its extended atmosphere reaches far into space. Even if Earth's core orbit remains outside the visible photosphere, the tenuous outer layers of the red giant can extend close enough to create drag. Friction between Earth and this sparse stellar envelope can remove orbital energy. If drag dominates over outward drift from mass loss, Earth will spiral inward. If outward drift wins, Earth survives as a remnant world orbiting just beyond the sun's maximum radius. The precise outcome depends on details of stellar mass loss rates and tidal interactions, subjects still studied through models and observations of other aging stars. But in either case, Earth's surface will have long since become unrecognizable. During peak red giant expansion, the sun's radius could approach or exceed Earth's current orbital distance. Its luminosity may be thousands of times greater than today. Even at a slightly expanded orbit, Earth would receive immense energy flux. Surface temperatures would not merely melt rock, they could vaporize portions of the crust. Minerals would break down, lighter elements might escape into space. Heavy elements would remain oxidized and altered by extreme heat. If Earth is engulfed, the sequence unfolds with slow inevitability. As the planet enters the sun's outer layers, drag increases dramatically. Orbital speed decreases. The path spirals inward. Tidal forces stretch the planet slightly, generating internal heating. Friction with stellar plasma strips away any remaining atmosphere and begins eroding the outer crust. Within the red giant's envelope, temperatures range from several thousand degrees near the surface to far higher deeper in. Earth would not survive long as a coherent body. Its materials would heat, fracture, and eventually disperse into the star's convective layers. The atoms that once formed oceans, mountains, and living cells would mix into stellar plasma, indistinguishable from the hydrogen and helium surrounding them. If Earth avoids engulfment, its fate is quieter, but still terminal. The sun, after exhausting helium in its core, will become unstable again. It will pulse, shedding outer layers in dramatic episodes. These layers expand into space, forming a glowing shell of ionized gas. From a distant vantage point in the galaxy, observers would see a planetary nebula, a luminous bubble expanding outward, lit by intense ultraviolet radiation from the exposed stellar core. The name is misleading. Planetary nebulae have nothing to do with planets in their formation. The term arose from their round appearance in early telescopes, but for Earth, the name carries bitter irony. If remnants of Earth remain, they will orbit within or beyond this expanding nebula, bathed in harsh radiation. The sun's core, now a white dwarf, will shine with brilliant intensity at first, though its total luminosity will be far less than during the red giant peak. The white dwarf will be small, dense, and hot. Surface temperatures may exceed 100,000 degrees Celsius initially, though with limited surface area, its total energy output will be modest compared to the giant phase. Over billions and trillions of years, the white dwarf will cool. If Earth's core survives as a metallic and silicate remnant, it may continue orbiting this fading star in an ever-darkening solar system. The surface, once melted and reformed, will cool and solidify into a frozen shell. In this final state, Earth becomes something like Mercury today, but colder with time. No atmosphere, no water, no tectonics, just a scarred rock reflecting faint light from a dying ember. The timescales stretch beyond intuitive comprehension. From the first subtle warming of oceans to the complete transformation of the sun into a white dwarf spans roughly 5 to 7 billion years. The burning of Earth is not a moment. It is an era layered upon eras. The early phase unfolds quietly, hidden within gradual climate shifts. The middle phase accelerates with runaway greenhouse and ocean loss. The final phase erupts in stellar expansion and planetary devastation. Through all of it, physics remains consistent. Gravity shapes the star, nuclear fusion powers it, radiation transports energy outward, orbital mechanics governs planetary motion, thermodynamics dictates climate response, chemistry determines atmospheric transformation. There is no malice in the process, no intention. Stars do not choose to burn their planets, they simply evolve. In the distant past, when Earth first formed from the debris of a protoplanetary disk, the sun was fainter than today. The young planet may have faced its own paradox, a dimmer star that should have left oceans frozen. Greenhouse gases likely compensated, trapping enough heat to keep water liquid. For billions of years, Earth existed in a delicate balance between solar input and atmospheric regulation. That balance enabled the rise of life, complexity, consciousness. But the balance was temporary. Every habitable world around a main sequence star exists within a window of time. Too early, and the star may be unstable or too dim. Too late, and increasing luminosity drives sterilization. Earth's habitable window spans perhaps 6 to 7 billion years in total. Humanity emerged in the latter half of that window during a relatively stable climatic era. The knowledge that this window will close does not diminish its beauty. If anything, it sharpens it. One day, billions of years from now, under a red giant sky or within a stellar envelope, the last sunrise over Earth will pass. No oceans will shimmer, no clouds will glow pink at the edges, no wind will move across grass or water. Light will strike bare rock, perhaps molten in places, perhaps fractured and black. And then, eventually, even that light will change. The red giant will shed its outer layers. The glare will contract into a small, brilliant point. The sky will darken as the planetary nebula disperses into interstellar space. Atoms that once formed mountains and bones may drift outward, joining clouds that will someday form new stars and planets. In that sense, Earth does not end. It transforms. The burning of Earth is not annihilation. It is redistribution. Matter cycles through generations of stars. The calcium in bones, the iron in blood, the oxygen in breath were forged in ancient stellar cores. When the sun sheds its layers, it will contribute its own processed elements back into the galaxy. Some future planetary system may form from that enriched material. On some distant world, under another star, oceans may gather, clouds may form, life may emerge and look up at its sky, unaware that its atoms once orbited a yellow star called the Sun. How long until Earth burns? Long enough that no current civilization will witness it. Long enough that continents will rearrange countless times. Long enough that evolution, if life endures for a while, will reshape biology beyond recognition. But short in cosmic terms. Stars like the Sun live around 10 billion years in total before becoming white dwarfs. The universe itself is about 13.8 billion years old. Earth's entire habitable history occupies a narrow band in that vast timeline. Tonight, under a familiar sky, the ocean still breathes gently. The sun sets in soft colors. The warmth feels steady, dependable. Deep in the core of that star, hydrogen continues to fuse into helium. The core contracts by immeasurable amounts. Luminosity increases by fractions too small for human senses. The future burning of Earth is written there, atom by atom. There will be a last era of blue oceans, a last era of clouds, a last era when temperatures allow liquid water to pool and flow. There will be a last sunrise seen by living eyes, though those eyes may not be human. And then, across billions of years, the planet will cross thresholds from warm to hot to hostile, from hostile to molten, from molten to either engulfed or abandoned. In the end, silence. Not dramatic silence, not explosive finality, just the quiet continuation of physics after life has faded. The sun will dim into a white dwarf. Earth, if it survives, will cool into a frozen relic orbiting a fading ember, and the galaxy will continue, indifferent and immense, carrying forward the atoms of a world that once burned beneath a bright yellow star.